Hello students, welcome to our next discussion on the topic of precipitation. Now that we have learned how to estimate how many number of gauges we would require in a particular area, in this video we are going how we should prepare the precipitation data set once it is available from different gauges, what kind of corrections we need to do because typically we would be dealing with the watersheds that would be of size all the way from 100 square kilometer to a few 100,000 square kilometers. Specifically, if you look some of the basins like Ganga River Basin or Amazon River Basin, which span to great dimensions. So we have to present, correct, and also check for consistencies. And finally, there may be multiple gauges that may be present in a given watershed. So we have to also come up with the average representation of precipitation in a given area, and we will learn some techniques around that where arithmetic averaging would not work, how we should do that. So whenever we talk about preparation of data, we are essentially talking about two parts, where first part would deal with finding the replacement of missing data, and second one would be checking for consistency if we have the complete data available at a particular gauge. So to motivate the example of missing data, let us try to understand it with help of an example. Let us say that in a given watershed, there are four gauges that are present. So one, two, three, four, and all of them are making readings every year. However, in a given year, the gauge that I'm highlighting in yellow, it goes bad. So it is not able to make any recording in a given year. So we are just dependent upon the three gauges. Now this particular gauge must be there to make sure that we are meeting the standards that we discussed in our last video, that depending upon the terrain or variability of precipitation, we need to have minimum number of gauges. Now, what we should do that now we have lost one gauge in a given year because of some problem at a site, how we should find the missing value so that our records are complete. And if somebody wants to do some statistical analysis for our watershed or even for operational understanding to estimate return levels to design the structures, we need to have the completeness of data set. So the first method is as simple as taking the arithmetic mean, that okay, this particular gauge has gone bad, but we have data at these 3 points in a given year. Let us say that that year is 2019. So what we will do, we will simply say that if precipitation here is P1, precipitation here is P2, and precipitation here is P3, all taken in the year 2019, we will use the average of P1 plus P2 plus P3 divided by 3 as a proxy of data at the station X. However, this method would not be particularly useful and errors would be high if the variability or differences in the normal precipitation that we observe at station X versus the precipitation that we observe at sites P1, P2, and P3 is high. To do that, we propose a method of normal ratio. And what we do in normal ratio method is that we account for the ratios of precipitation that happened at the site X and at site P1 for which record is available, and we will keep on taking those ratios. So let us say that we are given an example where the normal precipitation at site A, B, C, D are known as 80.97, 67, 76, and 92, and so on. However, in one of the years, that is in 1985, the station D was inoperative and data was only available at site A, B, and C. Now we have been asked to compute that what would be the rainfall at D on in that year. One way is straightforward, that is we just take the mean of precipitation that has happened at site A, B, and C and say that the precipitation that happened at site D in 1985. But first of all, let's check for the variability. If we look into the variability, the percentage difference that has happened at site D for which data is missing in year 1985, and another station where the precipitation that was observed was lowest, which was 67.59, can be computed as 92.01 minus 67.59 divided by 67.59. Now, if this difference is greater than 10%, and to calculate percentage, we'll always multiply it by 100. And if this difference is greater than 10%, then the method of simple arithmetic mean may not be useful. And that's where we have to restore to normal ratio method. And what this normal ratio method says, it says that if you have to estimate the precipitation at site D, so look at the value of precipitation when this site D was working and multiply it with the precipitation at P1 in a year in which data of P has to be estimated, divided by normal precipitation that took place in a year for which data record is complete. So here this is ND, so this has to be N1 plus P2 N2 all the way till PM NM, and divide this by the number of sites or number of stations that were fully operational in the year from which this normal precipitation is taken, which is M in this case. Now, if we plug this formula into the problem that we are looking at here, our M would be equal to 3 because M corresponds to number of gauges that are working fully in a year for which we are looking for the missing value completion. And this is the year 1985. Hence, our M is equal to 3. And now ND in this case would be that particular value that was known when site D was working. So our ND would be equal to 92.01. And P1 upon N1 can be calculated as the ratio in which we have to estimate the missing value, and that would correspond to the gauge A. So these ratios would be calculated as the ratios for each gauge separately. So it would be 91.11 divided by 80.97 because this was the value of N1 in the year when the value of normal precipitation at gauge D was known. Similarly, we can calculate P2 by N2 as 72.23 divided by 67.59 and so on, and we will plug this back into this particular formula, and that should be the best representation of missing value of precipitation at site D that we can obtain. So this is a problem where we have plugged in the missing data. Another kind of situation that arises in the field is that what if there is a lack of consistency in the record? For example, we have a watershed in which again four gauges are located. So I am drawing this ideal circular watershed. So let us say there are 1, 2, 3, and 4 gauges are there. And what happened is that in one of the years, and we have data record for long time, that is for this watershed, we have data available for 30 years of period. However, what happened that in 1985, again that's our year, and this record is available all the way from 1970 to 2000. Somewhere in 1985, somebody went to this site D and replaced or displaced this particular water precipitation measuring gauge to a new position. Now, when the records would come, we would only have information about four gauges, and we would not have any idea whether that particular gauge was moved or everything was okay with that. So we have to make sure that our data is consistent. Not any external forces have impacted the quality of our data. And to do that, we make a use of double mass curve. Please remember this name. This is very important, and it would be asked in various competitive examination or in fundamental hydrological interviews if you are preparing for one. So double mass curve is a very fundamental aspect in the context of precipitation in engineering hydrology. So what we do in double mass curve, the reason it gets the name double mass is that on both on x-axis and on y-axis we have the measure of precipitation, and that's why it would be mass, because if you know depth of the precipitation, you can always calculate what is the mass per unit area. And here also we have mass. But what is the difference in x-axis and y-axis? Let us look carefully. Now, on x-axis, we have the accumulated annual mean of 10 stations. What that means is that let us say there are multiple stations, and here I am using the textbook example, which says that let us say that instead of 4 there are 11 stations into our watershed, and one of that particular gauge is the one that is disturbed or for which we are checking the consistency. So 10 plus 1 is the count. So for all other 10 gauges, what we will do, we will calculate the mean precipitation for each gauge, and we will take the mean of total precipitation for these 10 gauges. So basically for each year, we will sum up the total precipitation I equal to 1 to 10 in this case and divided it by number of gauges. So that would be the precipitation or the average precipitation at all the 10 sites that we are getting in a watershed. Now, what does this word accumulated mean? Now, what we will do is that in anti-chronological order, that is, if we have to check the consistency of records from 1970 or 1954 to 1970, what we will do, we will take this average value that we obtained for those 10 gauges and measure it and say that that is the value of for 1970, and we would say that is x1. We will do the same exercise in 1969, that is we will look at all other 10 gauges, take their average precipitation or mean precipitation, and we will say that it is x2. But when we are talking about accumulated annual mean, we would say that in 1969 we would use the value of x1 plus x2. In 1968 we would use the value of x3 plus x2 plus x1, so that this function is monotonically increasing in anti-chronology. Anti-chronology means that latest year came at the bottom and the oldest year would come at the top or farthest from the origin, and that's what we mean by anti-chronological order. So the key takeaways from double mass curve is that both on x-axis and y-axis we are going to have the depth of precipitation, which is equivalent to representing mass of precipitation. As we know, the density of water is typically 1000 kilogram per meter cube. Another important characteristic is that it would always be anti-chronological. The year that has happened recently will come closer to the origin. Year that is farthest away or has happened in long back ago would go farthest from the origin. So what comes on the y-axis? It is the accumulated annual rainfall at site X, whatever is of interest. We have to make sure that the units are consistent. So if you are measuring this in meter, the units of both axes has to be in meter. If you are measuring it in centimeter, units have to be in centimeter, and so on. And since these numbers would be pretty big, typically we say that this represents the 10 to the power 3 or 1000 centimeters. So if I write 10 here, that typically would mean that it is 10 into 10 to the power 3 or 10,000 centimeter. But for sake of brevity or compactness, we will write the numbers in 10, 9, 7, and so on. So on y-axis, the station at interest, we will do the same thing here, that what is the precipitation that has taken place in 1970, 1969, 68, 67, and so on. And mind it that when we are plotting this y-axis, we are not accounting for any other stations that we have already accounted for on x-axis. And when we plot it, you would see that wherever the disturbance or perturbation has changed, that would be evident on graph paper that the slope of our plot between these two masses will change abruptly, and we say that this is an year of significant change. Now in this example you see that after 1963 there was a consistent pattern here that everything was falling in a straight line. Before 63, all the points were still falling more or less in a straight line, but there was a deviation in slope. And that would mean is that we have to bring these values down such that we are able to apply the correction. And one way to apply that correction is that we should correct the slope of the line that has departed before 1963. To do that correction, what we say is that the corrected value PCX is equal to the value which has departed from the consistent pattern, and we multiply it by the respective slopes. So if this is the base which represent as B, we can clearly say that to make these slopes consistent, we should multiply all these points by the term which is lesser than 1, as we have to bring these values down, and that should be C upon A to make that sure that the slopes are consistent. If MC represents the slope of previous case, it would be simply C by B. If MA represents the slope of departed line, it would be simply A by B, and hence when we divide it, the correction PCX comes out to be older value PX, which has to be checked for consistency multiplied by C times A, because these B and B would cancel out as soon as we put them in denominator. There will be one simple example in your assignment, and this concept would become very clear that how to solve these kind of problems. And again, I say that double mass curve is an important concept. Now that once you have corrected the data at different gauges for consistency, you have to present this data for engineering applications so that a site engineer or a design engineer can understand how they can use certain aspects into the design. So the two most commonly used data representation include, one is mass curve, where you say that, let us say that on x-axis we have time and on y-axis we represent the accumulated rainfall. Now, one thing that is consistent in double mass curve and mass curve is that whenever we are talking about mass curves, we are always talking about precipitation that has accumulated. And even in this case, we plot the total number of, so for example, when this storm started at t equal to 0, rainfall just started, total precipitation that will accumulate is 0. As the storm is passing, we will have some accumulation happening, that is total would be T1 plus T2 plus T3, the amount of precipitation that has happened at T1 and T2 and T3. And now then when there is a sort of a plateau, when no precipitation happens, we will have a flat line here. But again, it will start increasing as another storm comes. And finally, when precipitation event ceases or the storm goes away, we will have a flat line going parallel to x-axis. This is called as a mass curve. Then also second important curve that we deal in representing precipitation, or graph that we deal in with precipitation, are called as hyetographs. So what are hyetographs is that most of the times we will express precipitation as intensity, and intensity is always measured depth per unit time, and typically it's centimeter per hour or inches per day. And what we do is that on x-axis we have time and on y-axis we have intensity. That is, let us say that in first half hour, 0 to 0.5 hour, intensity of precipitation was 2 centimeter per hour. From 0.5 to 1 hour, the precipitation happened to be at the rate of 4 centimeter per hour. And if somebody asks us what is the total volume of precipitation that has happened on 1 centimeter square of area, we can quickly say that here we have 2 centimeter per hour. That would mean that 2 centimeter multiplied by 0.5 should be the depth of precipitation that happened in first half hour, plus uh, 0.5 times 4, or 1 plus 2, that would mean that in half an hour 3 centimeter of precipitation has happened. In 1 hour 3 centimeter of precipitation has happened if our given hyetograph looks like that. And the use of hyetograph will become more clear when we will talk about losses or abstractions, specifically phi index or W index that deals with the losses. But remember the name hyetograph, it's not hydrograph, it is hyetograph. Hyto represents the precipitation, and graph representing precipitation intensity becomes hyetograph. Another important representation that we typically use in large watersheds are called as isohyets. Isohyets. So what ISO means? ISO means same. Heights means precipitation. That's why we said it's a hyetograph. So isohyets would mean the contour lines that represent the same value of precipitation in a given watershed. So whenever storm passes, it passes in a pattern. So there would be certain points where you would have more or less same intensity or same depth of precipitation that has happened in a given period of time, versus as you go away from the reference point, these intensities will keep on varying. So we would say that, let us say that this is one isohyet where the precipitation depth was 8 centimeter. Similarly, another isohyet had the depth as 10 centimeter. Here we had 12 centimeter. Here we had 14 centimeter. And based on this, we say that this is an isohyetal representation of precipitation that has happened into a given area. Now, when we will go towards averaging of precipitation, we will discuss something called as isohyetal method, and use of isohyets would become clear. Now, finally, to conclude the discussion on the representation of this data set, sometimes we have is that we have to deal with the time series of data set. And we will see that when we deal with the time series, especially if time series is at much finer resolution, let us say hourly or daily, the undulations in precipitation patterns would be high. For example, if it is hourly data, in first hour some major storm passed and we got this peak, and then there was a peak, there was a silence, another storm is happening. So we would have some undulations like this when we are talking about precipitation. When we are talking about monthly precipitation, we would have some months which would have high precipitation values, some months would have low precipitation values, and so on. So there would be large fluctuations, or we say that there are certain events of high frequency that are present whenever we have long enough of time series. So to smoothen it out, we typically use the technique of moving average. So what we do in moving average, we select a window size over which we will average out. So let us say that for this time series, we select a, a window which is of size of 12 hours. So what we will do, we will take this window and put this on our hourly data of precipitation, which is in centimeter, and this is P. And we will take the average of all the data points that we have, and we say that this is the representative value for these 12 hours, and we will center it at the window. That means we will say that this time series would now start at 6 hours and the value is representative of it. Now we will slide this window by an hour, and now we will cover 1 to 13 hours. So initially we were covering 0 to 12 hours. Now our slided window will cover 1 to 13 hour, and again we will take the average and we will keep on doing it until we reach the end of time series. And as a result of which, instead of having all these high variable events, we will have a smooth representation of our time series. One thing is for sure, that we will lose a lot of information whenever we do this smoothing, but it clearly tells us if there is any trend, both upward or downward, is present in our watershed or not. So this is all about how we use various techniques to represent the data sets. We will deal with the extreme precipitation events separately, where we will talk about depth duration curves or intensity duration curves. But this is the representation of average amount of precipitation that has happened in a given watershed. In our next video, we will discuss how we should average the precipitation, and then we will also lay the foundation of extreme precipitation event analysis. Thank you.